Happy Tuesday, my friends. We're going to do a little elementary school throwback today, and we are going to talk about phases of matter. Another word that you may have used in the past is states of matter. I don't think one is better than the other. It's just whatever comes out of my mouth at that time. So those are kind of sort of the same thing. So when I say states of matter, the three biggies are solids, liquids, and gases. And everybody says, hey, what about plasma? You're totally right. But we don't give it the credit that it's due for sure. But that's definitely something I bet you could talk about in physics. So if that's something you're interested in, check out AP Physics 2. Dr. Purpose teaches it, and she can hook you up. So you should have already done the solid, liquid, gas manipulative, where you got to move around the little pieces and put them in their places. We just wanted to see how successful you were. Now, I know I just said that this is elementary, but some of those words on those cards were very much higher level than what a fifth grader could understand. So we don't expect that you got them all in the exact right place, but I bet you did pretty well, which means we don't need to camp out here for very long. So here is what I call my answer key to that activity. They don't have to be in the same order, but they do have to be in the correct column. So let's talk about some of the things that I think kids miss throughout the years. This word rigid means that it's really tight and compact, and it's not going to move. It's hard as a rock, and you could chip your tooth on it if you tried to bite down on whatever it is, because it's pretty stationary and it's not going to move or flex at all. Incompressible, this word right here, incompressible, gases are compressible. I say the word compressible means you can squish it, okay, which means I can't squish a solid and a liquid. They are what they are. If I take a wood block, I can't squish it and make it flat. It's not going to work. I can cut it, but that's not the same thing. Compressible means I can squeeze on it and I can make it fit into a smaller space. And that is so not true with a block of wood. Now for gases, that is totally true. We take all the air out there and we squeeze it into a scuba tank, okay? And now we have highly compressed air in there, and it can come out as bubbles, and it can help our scuba divers breathe. That is very good for them. And so that is a word that maybe fifth graders probably didn't talk about, but that is something we want you to understand. You're going to see a lot of words like this: definite volume, definite shape. Okay, so if something has a definite volume and a definite shape, it does not change. Okay, but over here, liquids have a fixed volume, but no fixed shape. Think about a gallon of milk. A gallon of milk takes the shape of the gallon until you drop it on the floor, which we have done in the garage once, and it was the messiest mess you've ever seen, trying to clean milk up off of the garage floor. And so that milk literally covered the floor, the walls, the refrigerator, wherever the milk splattered, that's where it went. Same amount of milk, still a gallon of milk, just no longer in the gallon jug. Now it's all over the Dooley's garage. All right, and then you've got gases. There is no volume and there is no shape. The shape and the volume all come with whatever container you put them in. They completely fill that container completely. In a solid, we've got particles that are tightly packed, regular pattern. Those particles that look like this, they don't move. They're not free to flow or bend or flex at all. So they're locked in place, but they still have energy, and they want to get rid of that energy, and they want to move. They just can't go anywhere. Think about the last time we had a lockdown drill, and your teacher puts all of you huddled up into one part of the room, and you're crammed in this corner out of sight so people can't see you through the window, and you're all crammed there. You want to move, but there's nowhere to go. And so you're all just stuck. And so these particles, they vibrate. because of it. So they aren't perfectly still. They're kind of vibrating in place, but they're so tiny. We're talking about atoms, y'all, okay? That you're not going to feel that vibration because they're too tiny. So these particles are vibrating all over the place. The melting and boiling points are above room temperature. Think about that block of wood. Think about a block of lead. If I want this lead to melt or boil, I got to get some flame, right? And I've got to put all of that energy into that lead. So he might have a melting point or a boiling point of like 1400 degrees. All right. So that's going to be really hard to get that into a liquid or a gas phase. Your liquids, however, they're close together, but they're not really organized, okay? I say that these guys flow. Liquids flow. They vibrate, they slide past each other, they're fluid. That's another word you hear for liquids, is fluid. You can add any of these words to a text box and put them on this page, so it'll help you remember some of the things we talked about today. I know it's going to take some time to get used to that notebook, but just keep plugging away. You'll get better at it, and in a month we'll forget that this was hard, okay? It's going to be the best thing that comes out of your year in chemistry is this beautiful notebook at the end of all of this torture. And then our melting point. So when the melting point is below room temperature, that means liquids are easy to melt. Guess why? They're already melted. They're a liquid. So they melted a long time ago at some really low temperature. And then they're hard to boil. Oh, I got one for you. Water. It's easy to melt because you put an ice cube in your hand and boom, it melts. So it's easy to melt, but oh my gosh, I want to make mac and cheese and that water is never going to boil so I can put my noodles in. Oh, it's taking forever. That's what that guy means right there. And then we get to gases where they have no fixed shape. They are not arranged regularly. They are all over the place. Think about the last time you passed gas. Don't act like you don't do it, okay? You passed gas. The person next to you might smell it, and you're hoping not because you don't want to be mortified in the 10th grade. And so you pass some gas, and it separates, and it literally dissipates throughout the room. So the person next to you might smell it, but the guy in the opposite corner isn't, because that gas is going to spread equally throughout this classroom, which is its container. These molecules are moving at very high rates of speed, and they bounce off the walls and they just keep going, and they don't slow down. They don't lose energy when they collide, which is very rare and very unique to gases. And look at their melting and boiling points. That means they're easy to melt and they're easy to boil. So they're gases. They don't want to be super duper cold, and so they melted and boiled at really cold temperatures. And so air is a perfect example. You can liquefy air, but you're going to have to cool it down a lot. And you can make air a solid, I suppose, but you're going to have to cool it down even more. And so it's going to be a little bit difficult. So this next slide kind of summarizes some of those same things. A few new words that I wanted to point out is density. Okay, solids have a high density, a lot of stuff crammed into a small space. There's not a lot of space between the molecules, whereas your gases have low density because they tend to spread out in the opposite direction. The gases have the most kinetic energy. They can be compressed, and there are no forces of attraction between the particles. They don't even care if they're next to each other. Whereas your solids have a lot of attraction between its molecules. So a minute ago, I told you that liquids flow. Okay, you know that water flows, but gas also flows. Anything that flows is a fluid. So a gas is a fluid also. That is just weird. So here's where the 5th grade part comes in. I'm pretty sure you know most of these words, but I know there's a couple that you don't. If we took ice and we changed it into water, we know that the ice melted. We can take the water, we can heat it up, it evaporates or it boils, and it turns into water vapor or steam, right? That is not hard. Then you take that water vapor or steam and you cool it off at night. It condenses. That's why we have dew on the ground sometimes in the mornings. And then we take that dew and we get it even colder, and that dew will freeze and all of our plants will look frozen in the morning. So those you're all familiar with. The one that is bizarro, that is kind of fun to see, is when something that is solid skips the liquid phase and goes directly into a gas. And the word for that is sublimation. Sublimation. So you need to know that word, that when solids go directly to gas without liquefying, that is called sublimation. One of the substances that does that you're familiar with, carbon dioxide, also known as dry ice. Dry ice, you're not going to see it as a liquid in your world because you don't know how to liquefy it. But guess what? I do. So this might be one of the first things we do when we come back in September, is we might do a little mini dry ice lab so I can show you what I'm about to explain on the next few slides. So that dry ice starts out as a solid and it goes directly to carbon dioxide gas. And we can take that gas, cool it off way below a regular freezing temperature, and that word is called deposition, and it goes back into the solid phase. So deposition is when the gas goes to a solid. Sublimation, solid to a gas. Just remember, sublimation starts with an S, so it starts with solid, goes to gas. I don't have a good one for deposition. Sorry about that, friends. Okay, so we're gaining energy as we go to the right, so plus energy, and we're losing energy as we go to the left. This is the same exact thing in a different way. I just think that some of you were taught this with this graphic, which is fine. I just wanted you to see that, hey, remember, you learned this, you just forgot. And here's those words that aren't on the tip of our tongue that we have to practice and remember. There's another way. This is brand new information, so at this point we need you to pay attention. And so there is this is another way to look at phase changes. So a heating curve will show you all of the phases plus the phase changes. And so I hope you can read cursive. And so on the y-axis over here, we have temperature in degrees Celsius. We don't like Fahrenheit in science. I talk about it because I know you're familiar with Fahrenheit, but when we actually use a thermometer, it only will measure in Celsius. So your temperature is always going to be on the y-axis in Celsius. You might see different things on your x-axis. You might see time, you might see reaction progress, or you might see something called heat energy. So all of those different things might be on your curve. So just know, hey, some time is passing by. This reaction is proceeding. We're adding energy to this reaction. So imagine this. If we're down here at point A, according to that temperature scale right over here, is that considered a hot or a cold portion on our graph? Well, compared to all of the other points, this is the coldest point, for sure. So what does that mean about point F? This is the warmest point. So that's why we call it a warming curve, because as this time goes by, we're going from cold temperatures to warm temperatures. So if we're at really, really cold temperatures, what does water tend to do when it gets really, really cold? Is it a solid, a liquid, or a gas? Hopefully you're saying that, ooh, it's a solid when it's cold. It turns into ice. You're totally right. So this would be the ice portion or the solid portion of my graph. So what's happening as we move up the graph? Well, what's happening to the y-axis? We went from the coldest temperature and our temperature rose to about here. So the temperature went up. Well, what happened to the heat energy on the x-axis? Well, we started here with no energy or a little bit of energy, and we went to here. So we also gained energy. So the temperature went up because we gained energy, and it affects our thermometer. Here's where it gets weird, my friends. Pay attention. Now that I'm here at point B, and I'm going over here to point C, what happened on my y-axis? What did the temperature do? Well, the temperature, I'm going to write it way up here because I'm going to put something else on that line. The temperature stayed the same. The temperature did not move, but look what's really, really odd. What happened to the heat? It went from B to C. So we added heat. So the temperature is staying the same, but we're adding heat. That is true during a phase change. During a phase change, when it's changing from one phase to another, the temperature remains the same. I'm telling you now, you gonna see that again. During a phase change, the temperature doesn't increase, which is not what your brain tells you should be the right answer. But that is what's happening. And I'll give you an explanation in just a minute. So if we're at solid at B, what is that solid about to do when you add heat? Well, I hope you're saying it's about to melt. That ice is about to melt, and you would be right. So while it is melting, ready? Chicken Express cup. Okay, Chicken Express. The only thing in a Chicken Express cup, as far as I'm concerned, is sweet tea. Now I'm about to make some of you real mad. I don't like sweet tea. I don't like it. It's gross. It's nasty. I can't do it. I've tried. Can't drink the Chicken Express tea. Okay, I could have made the cup yellow, so that would have been more true to form, right? So I've got some Chicken Express sweet tea inside that cup. Here's what I know. There's two phases of matter in that cup. There's the ice portion, and there's the tea portion. If there's two phases of matter, what does that mean? It means the ice is turning into liquid, right? The ice is melting. Well, if there's two phases of matter inside that cup, ice and tea, that means the temperature inside the cup is staying the same, which is actually exactly at 0 degrees Celsius. Ice will start to melt at 0, and it will stay at 0 until the last speck of ice is gone. When the last speck of ice is gone, oh look, we're at point C, and what is going to happen? Boop, 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 boop. So we're going to go up this hill. We're going to land at point D. So again, the temperature is increasing, the heat is increasing. This is what we call the liquid phase, or this is water if we're talking about H2O. So the only time the temperature stays the same is on the flat line, but it always increases with the heat on the diagonal line. So that water gets hotter and hotter and hotter and hotter, and if that water gets hot enough, what will that water do? Let me hear it. You're being quiet. I don't hear you. That water is going to boil. Okay, so sometimes we don't say it boils, sometimes we say it vaporizes, turns into a vapor. And so again, what's happening to the temperature? The temperature is staying the same. The temperature is staying the same, and the heat is increasing. So we're adding heat, and the temperature is the same. Once all of that water boils, what does it turn into? Well, it turns into steam or gas. And so that is the top portion where it is the warmest. Have you ever heard that a steam burn is worse than a hot water burn? Well, here's why. I'm going to change colors to green. Here's a steam at its lowest temperature. This is how much energy it has, somewhere right here. Well, here, maybe it's boiling water. This is how much energy it has here. Who's got more energy? That steam. So that steam is going to be very, very dangerous. And people that work at hydroelectric power plants or nuclear power plants, this would kill them. If a boiler ruptured and all the steam came flying out, it would kill those workers. So they have to be really, really careful and know what they're doing and protect themselves. But this is how a heating curve works. We say that anything on the diagonal line has kinetic energy, and anything on a flat line has potential energy. Those are some throwback words from middle school, right? So kinetic means moving, and potential means stored. In our dream world, you can write all of this down. You have paper, hopefully, at your house. You can follow along in your notes and write your own notes. Take a photo of those notes. Email them to yourself, to your single sign-on. Save that picture in your OneDrive. Upload it onto a slide in your digital notebook. Boom. You've got my notes that were preloaded, and you've got the ones that you took, and you've got everything you need. And we will practice that more. But you are always welcome to do that, and I will teach you how. So same thing we just said, but it's called a warming curve if it goes this way. So guess what it's called if it goes this way? It's called a cooling curve. But really what would happen is we would take this whole graph and we would flip it over, and we would start up here at the top and we would zigzag all the way down. Okay, and all of those phase change words are still here, like condensation, freezing, melting. Did you know the freezing point and the melting point are the same point, but they're just going opposite directions? Sometimes that blows up kids' brains. They're like, what? I'm not lying. If this was water, water freezes at 0 degrees Celsius or 32 degrees Fahrenheit. If this was ice, ice melts at 0 degrees Celsius or 32 degrees Fahrenheit, y'all. It's the same point. It's just going opposite directions. I really like the little diagram pictures that they have too, showing you what happens to those molecules as they gain energy and they move further apart. And every substance has one of these. Water has one of these. Carbon dioxide has one of these. But their lines will be different lengths based on how much energy it takes to separate out those particles. So nobody's warming curve looks alike. It's kind of like a fingerprint for a chemical. Every chemical has its unique fingerprint and its unique warming curve. Here's another one. Notice how long this liquid phase is here in the middle, okay? And how small this solid portion is. But again, looking at the same thing, just in different ways. The last diagram we're going to talk about today is called a phase diagram. Y'all, I have never been known to hold my tongue. I say ridiculous things. Somebody taught me this and it's stuck in my head for life. They called them butt diagrams. Like your butt, like you're sitting on your butt, diagrams. Look at the picture. Look at it closer. Do you see it now? Okay. I'm not even going to tell you what this is called. You can guess. But that is why people think it looks like a butt. All right. Just like with a warming curve, every substance has its own phase diagram. The only difference is these sections will be different sizes depending on which chemical this is for. The other thing that will be different are the numbers that you see on the axes. So these numbers are only for water. Now I'm going to explain what all of these mean. And so notice that ice is all the way on the left-hand side. Well, think about this. Ice has what kind of temperatures associated with it? Well, you know, ice is cold. right? So if we look down at our axis, this is the coldest portion of the x-axis. So this section on the left is always going to be your solid portion. Always and forever, that is your solid portion. As you move from a solid and you start warming up, you cross the line. That line got us into the liquid phase. And as you take that liquid and you warm it up, you crossed another line, which is a phase change. And so you're now in the gas or the vapor phase. And so it's just another way to look at a warming curve, but we have a new variable that you're not quite familiar with. The P stands for pressure. And we're going to deal a lot with pressure in the gas unit at the end of the second semester. For right now, all you need to know about pressure is that 1 atmosphere of pressure is considered normal. So I'm sitting up in my classroom all by myself today recording videos, and the pressure in this room, normal pressure, is really close to 1 atmosphere. The weatherman reports the pressure every night. He reports it in inches of mercury. Some of you have heard of PSI. That's pounds per square inch. That's 14.7 PSIs. Normal on the weather would be 29.92 inches of mercury, and those all correspond to this 1 atmosphere of pressure. Why is that important? Because what we want you to do when you see one of these phase butt diagrams, you need to find the normal pressure and you need to draw a line all the way across your graph. So right now on your PowerPoint slide, you can pause this video. You can go to your interactive notebook. Up at the top of your PowerPoint, one of your menu items will say insert. And you can insert a shape, and you can pick a line, and you can insert that line going across at the 1 atmosphere mark. The other one sometimes we see is 760 millimeters or 760 torr or 101.3 kilopascals. But we're going to tell you what normal is, but 1 atmosphere is normal. Every time that normal line crosses one of these phase lines here, that is the phase change. So this dot going from ice to water is the melting point when I'm going this way. This dot, when I'm going the other way from water back to ice, is the freezing point. So if I look at this dot and I go straight down, oh look, water's melting point and freezing point is 0 degrees. We already knew that, but now we're looking at from a pressure perspective rather than a temperature and energy perspective. So we're going to keep going across that line till we get over here. Now we're going from the liquid to the gas phase. What do we call that? That is the boiling point. And if we went backwards, I don't think this really has a word. It doesn't have a melting point, boiling point. This is just condensation. I don't think they call it the condensation point. They might, but I have never heard anyone say that to me in my life. What the weatherman talks about is the dew point. At what point will the gas in the air turn back into water and make my grass wet? So he will tell you that temperature. So that water's boiling point, oh looky there, 100 degrees Celsius. Again, we already knew that. So this is a phase diagram for water. So water sees the ice phase, the water phase, and the gas phase at normal pressure, but it's all temperature dependent. If you make the temperatures high, you see steam. If you make the temperatures really low, you see ice. If the temperatures are somewhere in between, you see liquid water. So what in the world is happening at this red dot in the middle of my page? This red dot here is called the triple point. This is really hard to do, but it's cool, and it's neat. And I might throw on a cool little YouTube video that's optional for you to watch if you would like to watch somebody try to achieve a triple point of a substance. Here's what this means, and this blows up his brains. That means I have a beaker. In that beaker, I'm going to put some water. In that water, I'm going to put some ice. And you're like, no big deal. I see that all the time, woman. Okay, but look what I'm going to do. Instead of normal pressure, the triple point is at a pressure of 0.006 atmospheres. That's basically no air in the container at all. Such low pressure, you couldn't breathe in a room with that low pressure. So we are going to drop that pressure like a rock. When we do that, okay, when we drop that pressure and we get it exactly at this temperature of 0.01 degrees, guess what else is going to happen inside my ice water? My ice water is going to boil. So I'm going to see ice, I'm going to see water, and I'm going to see steam all in the container at the same time. That only happens at the triple point. And the triple point depends on two things. It depends on the pressure and it depends on the temperature. If either one of those are off, you won't see it. You will just see two phases. Think of it from this perspective. Let me clean this up just a little down here. Okay, what if I lowered the pressure even more? What if I came down here and said I was at 0.003? Now as I draw my line across, what did I do? What am I going to call this? I'm going from a solid to a gas. That, my friends, is sublimation. I skipped this whole liquid portion entirely and I went straight to the gas phase. Well, guess what? Water doesn't do that unless the pressure is ridiculously low, and it's hard to do with water. And then the opposite of sublimation is that word we learned earlier, deposition. Those are the points you need to know. The critical point, we're not going to test you over that, but the critical point is the point at which it doesn't matter what happens to the temperature. At 374 or higher, water can only be a gas. It will not liquefy, even if you pressurize it. It won't do it. It's got too much energy. The molecules are too far apart. It's going to remain in the gas phase for the entire time. This is another example of a triple point diagram with all of the phases a little bit neatly placed on there rather than mine. It doesn't show you where normal pressure is, so I don't know what substance this is for. So if this was something like water, the line would be up here. If this was something like carbon dioxide, the line would be down here. But it's all pressure and temperature dependent. I thought this is a pretty neat graphic because we are going to start talking about physical changes tomorrow, and we're going to talk about chemical changes tomorrow, which are the fun part, which is why you joined chemistry. And then you've got your 8th grade words, you've got your potential energy, which is stored, and you've got your moving energy. And this just kind of shows you how everything coordinates, but it's all based on the energy of the molecules, holding them together, pulling them apart, and keeping things in sync. I'm sorry I talked a lot today. We covered a lot, but you've got a Canvas assignment that you can do and finish. You are going to do your work directly in Canvas. You're not going to put that in your notebook, and you are done for the day. I appreciate you. Log on to online tutorials sometime. Say hi. We might have a show and tell event this week. Maybe we'll show off our pets. Mine's the cutest. But I will see you soon, my friends. Take care.